Okay, so what we're going to do in this section is take a look at motion in one dimension again, kinematics, but we're also going to look at falling bodies and free fall and what that means. And to start with that, let's give a little bit of background about our understanding of gravity. So in Western philosophy, we had folks like Aristotle talking about what gravity means. And for Aristotle, gravity tied into his overall five-element theory of philosophy, where all objects were composed of elemental air, earth, fire, water, or ether. If it was up in space, it was made out of elemental ether and naturally moved in circles. And if it was and anything with elemental fire and elemental air within it had levity, and that naturally pulled it up. And everything with elemental water and elemental earth had gravity, and that naturally pulled them down. But the net effect of that for everyday life was that things that felt heavier and felt more pulled more strongly down were expected to accelerate more rapidly, to fall to the ground faster. And so he would give an example of like a hammer and a feather, and we can here use an example of a little steel ball bearing and a piece of paper, and indeed you drop them and the ball bearing lands first, the paper takes its time. But we note, though, that I take the same piece of paper and here we have identical pieces of paper, so I can drop them, they fall approximately the same way. But if I instead do what Galileo did as a thought experiment and reduce the effects of air resistance acting on the paper, we can see that the same weight of paper now gets to the ground much faster. And in fact, when I drop it with the ball bearing, they drop at the same rate. So that's our primary observation about gravity for right now, is that all objects accelerate towards the center of the Earth at the same rate. Well, we're talking about objects near the surface of the Earth. Well, we're going to modify that later on. We talk about how that really changes with distance from objects, but let's go with that for now. Okay, so what we call that process we call free fall. That is motion where all forces other than gravity are negligible. That is, we're able to neglect them in our analysis and still get results that are precise enough for what we care about. Let me and in the 1500s, Galilei, observes through a series of experiments that all objects fall with same acceleration from gravity. And we label that acceleration, lowercase g. That can also stand for what we'll later call the gravitational field. But g near the surface of the Earth, such as the realm that Galileo was able to observe, that has a rate of about 9.8 meters per second squared, or about 32 feet per second squared, if you want to kick it old school imperial units. So that's a thing that we will find useful in future analysis. We're going to have situations where it's only gravity acting on a thing, and analyzing that is going to do us what we need to do. In the real world, when you have an atmosphere like we do on this planet, there's always some manner of air resistance. Is it big enough that you care about it? Depends on the situation. So let's put that number over to the side here, and let's apply this to problem solving. So put that over here. Say g equals 9.8 meters per second squared. Okay. Downward. And again, we will find later that this value actually changes. It reduces with distance from the center of the mass. It's different on different planets, for instance. It's different on the moon, it's about 1/6 of that. On Mars, it's around 1/3 of that. If you were on some sort of space dirigible hanging out in the upper cloud layers of Jupiter, it'd be about 2.5 times as large as that. Can't stand on Jupiter, you just sink and get crushed. So, all right, let's play with this for a moment. So, for this problem, the introductory problem I like to do with free fall, I will have to take you back with heady tales of my misspent youth. So, when I was in college as an undergrad, I went to a school that was known to be a bit stressful, and the way in which the powers that be attempted to reduce that stress. Let's give us a little more space to play with here. Was they let us drop classes as late as 11 weeks into a 14-week semester with no penalty other than the time and money that you've spent. So you could get to that point and be under a fair bit of stress, and by the time it gets to that deadline, drop date, you're ready to release a bunch of stress, because if you are in a situation where your grades are suffering, you have to make that decision about whether you're going to be able to pull everything together and get the grades up at the end, screw your courage to the sticking place and whatnot, or are you going to cut your losses on one of the classes and then refocus on the remaining ones? And if you do that, then you got to make up that credit, or at some point somewhere else down the line. It's a loss of your time and money. So what we did in the dormitory I lived in, which is what this diagram is supposed to represent, was that we had a dormitory-wide water fight with the different sections of the dormitory allied against each other. And the main goal was to blow off steam and soak everybody. But we had a couple of secondary goals here. One of them was to soak the lounge of one of the dorms that a lot of the other sections didn't care for. But one of the nifty goals was to take the tower. And so the people who lived in the uppermost layer, their section, they were able to get roof access. Do not do this at home. And what they did was they took garbage bags and they filled them with water and they dropped them in front of the doors. This is not recommended. We did not, we will find that it does take a bit of time for them to drop, but somebody could have slipped. And this could really have hurt somebody and maybe even killed them. I don't know why we did this 25, 30 years ago, but it happened. I do not recommend this. But, here we go. They didn't actually aim for people. They made a big splash and you kind of got sprayed. So, now, we were kind of a nerdy school, and so you could imagine that somebody would have, sent some student to go down and gather intelligence on the plummeting garbage bags, on the defenses, as it were, and try to determine how long it would take for them to drop. And if they did that, and if we took away air resistance, then it might only take about 4 seconds for them to drop all the way. Now, air resistance exists. It was meaningful for this situation. It took more like 6 seconds. Again, people could scramble out of the way, but I do not recommend this. This could really get somebody hurt. To my knowledge, no one was. Still. There's a height that we don't know, that we could estimate by running the physics here. So I want to know, how tall was this building? I also want to know that if we drop them from rest, what gosh awful speed will they impact the ground at? Again, do not drop anything off of tall buildings. Bad move. But this is what we've got. So, in our problem-solving technique, we have drawn and labeled a diagram. We've listed known and unknown variables, but we've set them some things that may have told us some additional information that we didn't label here yet. For one, I've written up here dropped from rest. From rest means zero motion, zero velocity. And that's where we're starting to drop it. So that means that we have an original velocity of 0 meters per second. And if we're dropping and assuming that it's in free fall, then that means that the acceleration gets to be g, gets to be 9.8 meters per second squared. And so with that, we can go ahead and solve our problems. We take a look over at our equations. In this equation here, the only unknown is the final velocity. And in this equation here, the only unknown is our final position. I have not stated it directly in the problem, but we've set this up by choosing a coordinate system where the original position here is 0, and that's our original time. So downward is the positive direction, the way I'm setting things up here. You could make up the positive direction, but then that acceleration would be negative. That final height would be a smaller value than the original height. Maybe you're solving for the original height and you set the final height to be 0. Gets us the same information. So let's go ahead and do this. We'll go ahead and work the top equation first and find that deadly speed. So v final minus v original is acceleration times change in time. That's 0. So v final equals acceleration times change in time. So that's 9.8 meters per second squared times 4 seconds. So that's 39.2 meters per second, which is around 90 miles an hour. So that's, we're talking like major league baseball speeds, but for multiple gallons of water. Gallon of water weighs about 8.3 pounds. There's more than one in the bag. It's a bad scene. Okay, so again, do not try this on your own. Make sure your area is clear. Whenever you throw projectiles, make sure that nothing that you don't intend to hit is downrange. Okay. And then our height. Let's go ahead and use this one. So x final minus x0, which was 0, equals v0 delta t. Original speed's also 0, plus half a delta t squared. That tells us x final is 1/2 a delta t squared, or 4.9 times 4 squared, which is 78.4 meters. And that's it. Again, do not drop big things off of buildings where they might hit somebody. Okay.